So in my earlier lecture, we were looking at kind of more math perspective of dealing the things, right, rather. So it may become it may become difficult to you. I don't know your actual background, but is it okay? You're able to understand certain things from there, right? Okay, fine. I'll just continue that discussion and put it in a very intuitive way rather than taking you into the too much of intricacies of mathematics. Okay, the first thing is we are all engineers, right? Many of us are engineers. So I don't go into the definition of engineering, etc. But engineer's job is to solve real world problems, right? So real world problems, how do you solve real world problems? So the first thing is you model that problem. Okay, the moment the model means it is expressing in terms of mathematics. Okay, it could be mathematical equation, maybe rule based, etc. things, some kind of a statement. Rule means it's a mapping kind of a thing. So you have to express that in terms of some kind of a math. So it becomes either an equation, finally it becomes an algorithm to solve particular task, etc. will be there. Fine. So, but when you model certain physical reality per se, it is a representation. It is not an exact definition or exact of the reality. So that means we are expressing in math equations or whatever that may approximately represent or explain the phenomena. The moment when it's an approximation, there is an error. It is not the exact or the ideal, whatever we call like. There is an error. So when there is an error, I used to say to my students, engineers have to live with errors. Okay, engineers have to live with errors. In many cases, what we do is we minimize the error. Okay, what engineers can do is minimize the error. That's all. So you'll get a better performance, better efficiency, all these things you understand like that. So the first thing is put it in math equations and then try to solve. So the moment you model certain things, you get in terms of equations. Per se, it could be algebraic equations. So once the equation is there, you have to solve the equation. That's why for my students I'm saying, you have to solve certain equations. Okay, you cannot escape from that. Okay, so now if it is a scalar equation, per se, the moment equation becomes, there will be variables. Okay, variables means what? Something, suppose in when you frame when you form an equation, what becomes what? What is there is the variables are there. The variable means what? If you look at if you go into the history of our linear algebra and other things, they were looking. They were doing some kind of a trading, etc. things. They used to sell and buy in terms of not maybe at that time this currency and were not there. You buy certain horses by giving some cows or something like that. Kind of an exchange used to be there. Barter system. So like that you have to have variables. The variables you solve for the variables. So if it is a scalar equation, it is easy to solve. Okay, it is easy to solve means what? If I write like this, Ax. If I write Ax equals to b, it is easy to solve. Okay, what we write is x equal to b by a. We usually write. Okay. But what is this? This is A inverse B. A inverse B. So in the scalar case it is okay, but many times we have many equations. It is called system of equations, simultaneous equations. That means the solution satisfies all the equations simultaneously. So in that case it becomes a set of equations. You know how given the set of equations, how to represent in mathematics form. That becomes your Ax equals to b. That is a matrix version. Okay. Per se, for example, if I write a1 x1 plus a2, a11, a12, I write x2 equal to b1, a21, x1 plus a22, x2 equal to b2, etc. This you can write in terms of mathematics. I need not have to write that. You know what it is. But in the case of a scalar, you know that you take it for advantage as a real field, there is a definition of 1 over A. Unless A is 0, it's a problem there. Now the question of consistency comes here. I'll tell you what consistency is. In the scalar case, it is very easy. But what happens in the matrix case? Matrix case, this is A inverse B. You look at this and this, 1 over A and A inverse. In the scalar case, easy. Matrix, you have to have an inverse like, right? But inverting the matrix is not an easy thing. That's the problem. Inverting the matrix is not an easy thing, the first thing. The second thing is when there are so many variables here, these are all coupled, okay? X1, X2 is there, X1, X2 is there in each. They are coupled. Coupled you'll understand in a moment now. So the one way to solve the system means you have to uncouple the system. What do you mean by uncouple the system? Here the matrix is a full matrix like this entry, this entry, this entry is there. Entries are there, non-zeros. Okay, suppose the entries are such that you have something like a diagonal system. These two are zeros. You can directly read out the solution. You can directly read out the solution. No need to solve like. Okay. So now the question is, can I convert a given matrix A, which is a full matrix, means coupled in the sense every entry is there. Can I convert this into a diagonal matrix? That's one important problem. So why do you diagonalize? Because you can read out the solution. It makes our life easy. Okay, that's why entire linear algebra we talk about diagonalization of matrices. Okay. The system becomes difficult because the variables are coupled. That's the one. If it is 0, x1 is b1 by a11. Like directly you can read the solution like that. What is consistency of a system means? What is that? So for a system of equations, suppose if the solution exists, okay, it is consistent. The solution doesn't exist, it is inconsistent. For example, if I take, I just derive from this, okay, suppose Ax equals to 0. Ax equals to 0. What happens when A is 0? What happens when A is non-zero? Two cases are there. The other thing, what happens? Ax equal to b. Okay, suppose A is 0. What happens if b is non-zero? A is 0, b is non-zero. Okay, there are inconsistencies. That means something non-zero is not equal to 0. Mathematically wrong, that is correct. Suppose in this case particularly, suppose 0x equal to 0 I write. Okay, what is the solution? Can you imagine the solution there? Ax equals to 0 is the, what do we call? We call the homogeneous solution of the system, right? In a more math perspective, homogeneous solution. And if otherwise Ax equals to b is a non-homogeneous system. Okay, in that case, suppose we are all dealing with these problems in the real field. Real means this number, real number field. Per se, all coefficients are reals for me now. Okay, so 0x equals to 0, you take the equation, right? What happens to x? What is the solution? Can you imagine? Just you take any, including 0, any real number, it satisfies that equation. So the solution space we call, the set of all solution we call solution space. Okay, the solution space is the entire real space. In this case anyway, it is a one variable, so R1, entire real line is the solution space for this. If I substitute 7, it also satisfies, minus 3 also satisfies. So every real number is a solution to that one. Okay, that's the case. So there could be cases, okay, that's a very scalar, 1 by 1 system I used to call that. 1 by 1 system. This is 2 by 2 system. You can probably increase the order, 3 by 3. Sometimes it is a rectangular, sometimes it is a tall matrix, sometimes it becomes a, what is that? broad or whatever matrix, depending on the situation. Okay. So now, okay, probably you also understand by this, suppose Ax equals to B is our general case. It's a general case. Now Ax equals to 0 is a homogeneous system corresponding to the non-homogeneous, right? Now what happens? See here, this x, suppose if x satisfies Ax equals to 0, x is a solution. Correct, x is a solution. Now I am talking about set of all x, okay, such that Ax equals to 0. Okay, this becomes a set for me. This is a solution. This is a solution set for homogeneous. Homogeneous means, you understand? The B is a, no, you make it 0, 0, 0, 0. Instead of solving Ax equals to B, Ax equals to 0 you are solving. That is homogeneous. Now, the interesting thing what I want here is, you have understood vector spaces, right? You have understood R, R2, R3, etc. Euclidean planes. So what happens in this case? We know okay, I can draw a line in this plane, right? I can draw a line. I can draw the line anywhere. Here, here, or anywhere. Okay, there are particular lines you could see here, like they pass through the origin. They pass through the origin. You draw a line such that passes through the origin. Okay. Now, there is a notion known as a subspace. We know that R2 is a vector space. I am stressing here R2 because we have more visualization, things like that. I can draw something and then you can interpret, you have more intuition for R2 like that. So, but a single line if I draw, it becomes a subset of R2. Subset of R2. To call it subspace, we said there should be an origin in the set so that it becomes a vector space. Origin is a must like. Okay. So in that sense, what I am saying is, suppose this is your plane. If I write like this a line, precisely if you ask, this is not a vector space. Because it is not passing through the origin. There is no origin. There is no origin. So for it to be a vector space, I have to pass it through the origin. Okay, both are lines you call linear, etc. in your system perspective, etc. Right? But this is vector space because origin is there. This is not a vector space, but it is shifted by some other vector. That is called affine space actually. Affine space. So here most of, okay, a line can be an affine or a vector space. Okay, when we deal with systems and all pattern recognition problems, everything, no? What we suppose in the case of linear systems and linear classifiers, we deal with these type of lines. Anyway, what is a classifier? I just connect here. Classifier is nothing but a function. There are two classes per se. Classify, I have to draw a boundary between the two classes. It becomes a line or it becomes some curve, any curve. If it is a line, it is a linear classifier. It need not have to pass through origin all the time. But affine is okay, accepted. It is a cousin of vector space. Fine. This is a vector space. This is called homogeneous system. This is non-homogeneous system. You know that the solution space of homogeneous forms a vector space. That means 0 is a solution to this. If I substitute A into 0, it is 0. So 0 is a solution. 0 is in this set. Right? Now, Ax equals to B. Per se, let us go to the very scalar case. A is non-zero. B is non-zero. If I substitute x equals to 0, will it satisfy? No. So origin is not in the solution space of that. Okay, that means the solution to non-homogeneous system is lifted. Lifted what? Lifted, I mean you have the solution to homogeneous system that is being lifted. That's why you call solution of a general system of equation is Homogeneous system, solution of homogeneous system plus particular integral and all you call in your differential equations. Here it's a particular solution. It's a particular solution. So one is a vector space, the other is an affine space. Okay, this is how it is. Now, we said if it is a diagonal matrix, you can directly read out the solution like. Now the general question is, can any matrix be converted to diagonal matrix? This is a very important question in linear algebra. Can you convert a given matrix into a diagonal matrix? Usually matrices, there are square matrices and rectangular matrices. For the time being, let us keep apart from the rectangular case. At least take very nice square matrices. Okay? So can we convert any square matrix into a diagonal matrix is the question. Now let us look at some diagonal structures, how to go about that like, okay? For example, given a system of linear equations, what do we need? We need simple systems. Now system means what? It is a matrix. Matrix, okay? System is a matrix. Now we look at what are simple matrices, what are simple systems, equivalently what are simple matrices. Okay, so what are simple matrices? You know various types of matrices, right? Matrix means arrangement of numbers and rows and columns like that. Okay, a simple matrix is like, it may not be useful, okay? It's a zero matrix. Per se in 2 by 2 I write a simple, what is there? 0, 0. But it's not useful. Kind of a degenerate case, whatever you call. Next simple is what? Next simple is, okay, not a simple matrix is some A, B, C, D. All are non-zero. We want entries to be 0, but not all. See, there is something. We don't want all entries to be 0. We want some entries to be 0. Many times we call that as a sparse. Sparse, right? Okay, we want a small number of entries which are non-zero. Okay, like that. So, next simple case could be a triangular kind of a case. From this to this. This is useless kind of. I can have 1, 2, 0 and 3 like. It's a triangular matrix. It is more simple because if you have an equation corresponding to this, you know that you can read out the solution for this, back substitute and get the solution, right? So triangle could be either like this, or you can have this. One could be forward substitution, one could be backward substitution, you get correspondingly. Okay. Next simple case is your diagonal matrix. A and D probably like this, you write. Diagonal case. You know, diagonal is a very simple case because you are directly reading out the solution. Okay. There could be other levels of simple matrices like a symmetric matrix. 1, 2. How do you write symmetry? Okay, I can be a bit more appealing example because otherwise you say that all main diagonals are equal. Like this is a symmetry case. Next simple structure is symmetry. Okay, if you have a symmetric matrix, you have got something great. That's why all the time we strive to get symmetric matrices. Okay, in our Professor Rangaraj also, in one of the lectures he was giving examples of if it is non-symmetric matrix, he used to discard that while finding some features in biomedical applications. Okay, so more structure, more simple. Life is easy. Life is easy. So that you need not have to solve in this case. Here life is easy because somehow you can easily get the solution. There are techniques. If it's highly coupled, it is difficult, right? Now, from the linear algebraic perspective, there are procedures to solve given system of equations using your row operations, we call, right? elementary row operations. You might have heard elementary row operations. There's a row, you have to do elementary operations. You just tell that what they are. What are elementary row operations? Row interchange, multiply a non-zero scalar to a row, then to the second row or whatever, the next to the another row, you add scaled version of the other row. Okay, like that. These are operations. These are linear operations. Linear algebra, everything is linear, like linear operations. Then what happens? So given matrix, so it is something like this, which is not any of these cases. You try to convert that into these types of. If possible, it becomes a diagonal case like this. Otherwise, you will get a triangular, you are happy, right? You are happy. That's why that is called your echelon forms. Something non-zero, make everything below zero, etc. There are two things. One is echelon, another one is a reduced echelon. In the reduced echelon, you try to make it an identity type of thing. 1, you have to make that entry 1 below 0. Okay, like that. So, as far as the matrices are concerned, if you make it in given matrix into this type of, this is kind of an echelon form. Okay, echelon form. Okay. Here is more nice because you got a diagonal. Finally, if you can do 1, 0, 0, 1, wonderful. In this case, the matrix is invertible if it is a square and like this. That's how you compute inverse, right? What do you do to compute inverse? You have an appended matrix A, B, C, D. Here what do you do? How do you compute the inverse? So you make this matrix 1, 1, 1, 1. The other entries become the inverse of that. Right? Fine. So that's how we do. So we don't directly compute inverse. The point number 1 is like, you don't compute inverse like whatever we talked, what is that? Adjacent and determinant method of this one, or a Kramer's rule of type. Okay, even the higher dimensions or a higher order, it becomes tedious. You have to use elementary row operations to solve these type of problems. Okay, so you have got at least what is a simple matrix, what is not a simple matrix. Okay, what is a simple system, what is not a simple system. It can be a 1 by 1 system. You understand? 1 by 1 system, 2 by 2 system, 2 by 3 system is also possible, all these. Okay, so what we do is, from the given, I call this a difficult matrix. Difficult in the sense, to work out that is difficult. Otherwise nothing like that. Converting a system into a simple system. Now, when you convert a system to a simple system, you should not alter the solution of that system, right? The solution should be intact. You should not alter the solution, otherwise it becomes a different system. We call equivalent system. Okay? Given a matrix, can I have an equivalent matrix? Given a system, can I have an equivalent system? But the second system is easy to solve. That's what we are doing. We are converting one problem into another problem. Solution is the same, both cases. But the other problem is easy to solve. That's what it is. So, converting a given matrix A into B, to some B. B is very easy to solve. In a particular case, can I get B diagonal, what is that, identity matrix? It's asking too much, asking too much. Fine, in some cases you get, suppose if a matrix is invertible, and the consistency is what probably Dunn might have told you. When AX equal to B, you know that given matrix has rows, columns, okay? Set of all linear combination of rows becomes a row space. He might have told, I don't know. You know how to make linear combination. Row is a vector, column is also a vector. Now you can think of making linear combination of rows, right? That becomes a row space. Making linear combination of columns, that becomes a column space. So in particular here what happens is, it can be shown, if B lies in the column space of A, it has a solution. it has a solution. If B lies in the column space of A, it has a solution. So it is consistent. Okay, the another thing here comes is the rank of a matrix. That's more important. Like, okay, rank means what? Like, for a matrix, what is rank? Okay. How do you, okay, given a matrix, how do you find the rank? That's another question, right? If I give you a matrix, what is its rank? Okay. Now, when I say AX equals to B, it's a linear system, right? It's a mapping. What is mapping here? Suppose, okay, every matrix, there is X, right? X is the per se. For every X given A, there is B. Okay? So B, suppose B is like in the output, X is the input to this one, like. So this is in, X is here for me. Okay? Where is B? B is here. So what is the transformation? A is this. Okay? It transforms X to B. Right? Now, what is in our general set theory, etc., whatever we studied in +2 levels for engineering students, I'm saying, you are not considering these two are vector spaces, but there are some sets. Some sets. As you mature, what happens? These two, domain and codomain, we call, no? Domain and codomain, they become the vector spaces. So this is a set, right? The vector space is a set with a structure. This has a vector space with it's a set with a structure. These two become vector spaces. The moment there is a vector space, there is a 0 here in the domain. What happens to A into 0? 0. So this is the test case. What is a linear system? It's like an acid test. 0, if you put as input, the output becomes a 0. You might have seen that in your linear systems laboratory, resistor networks, etc. things. If you apply 0 input voltage or whatever, you should get 0 output. That is the test for linearity. That's obvious, because you see here, if I apply 0, the output is 0. If I apply 0, output is something else here in this case. This is non-linear. This is non-linear. That's why usually we confuse in the interview and other things, AX plus B. That B is causing the non-linear. That's fine. Most of your classifiers you write in terms of perceptrons, right? A naught plus A into W as a dot product or whatever. All are affines. Affines. That means I just try to relate that to the classifier also here, because that's your interest also, right? Suppose this is our feature space, right? Suppose height and weight of people, like maybe a gender wise, if I say male and a female. Feature is what? Height and weight per se. So height and weight are the two variables, right? Height and weight are the two variables. You start collecting data, right? This is height, this is weight, serial number. Okay, you start collecting data. This is measurement. Okay, 1, 2, you want your 100 measurements. That means 100 people you have to collect height and weight. This is your data collection now. This itself may be a feature, okay, height and weight. So data, height and weight is there. So height and weight are the variables now. These are the features, right? So you can, if you have time and patience, you can have 1,000. You should have, no? These days big data, and for every deep neural network and all, we need lot of data. And here also it is growing, not just 2 feature is sufficient. But for illustration purpose, and right on a plane I am taking 2 feature. You have so many feature, like thousands. You know, in deep neural network and all, feature, what is that numbers, like that much. Okay. Now, I want to just go to the covariance matrix there. That's why I'm just relating this. Height and weight as the feature. We start collecting the numbers. We have per se 100. I have selected 100 people and got the measurement. Now I want to have a covariance matrix here. Okay. Now height and weight being variables, I can do some statistics on this. I can calculate mean height, I can calculate mean weight, I can subtract them from each of this one. That is called centering, mean removing in statistics, right? Mean removed. I can remove the mean from them, both of them, remove the mean. Now, is there a correlation between height and weight? Usually when you choose characteristic variables for measurement, one thing is you at least try to measure independent variables as much as possible. But in reality, variables are dependent to some extent. Okay. Suppose, what I'm saying is, there's a height you are measuring. You are not measuring other variable which gives the information of height. That becomes redundant. We don't want that. We go for a complementary type of or such kind of a feature, which is not height itself. Suppose if I measure some other variable which gives the height information inside, it's of not much use in as far as classification is concerned. So we usually try to get more or less independent features. Getting independent is on the document only. It's in reality it's not possible. So height and weight. Now there could be some relation between height and weight. Okay, when there are two variables, I can look at correlation between height and height. Height is linearly dependent on height, right? Height is, suppose if I say height, it is one time height, right? This is a scalar here. Height depends on height, so correlation is 1. Height and weight, they may be correlated, maybe something like 0.5, 0.6, 0.2, I don't know, depending on the circumstance. There could be a relation between height and weight, so that you get a correlation measure there. Now you have a covariance matrix, that is, what is height and weight. You have to measure height and weight. So it is what? Height and height, maybe you get 1. Weight and weight, you may get 1. This may be height is related to weight, more or less fine. If it's a tall, your weight is more, that is said, right? So it may be 0.7. So if weight and height, the order is immaterial in this case, it is 0.7. You see here, you get a symmetric matrix. Okay. Correlation matrix, correlation which is measured from the covariance matrix here. So there are certain things in probability. We say correlation, there is a correlation as a concept is there. Covariance is also a concept, more of confusion like, but correlation is measured using covariance. Covariance is a concept actually. Correlation, you remove the mean, zero mean it becomes. It's a very simple relation between that. But factually what we have to say is, correlation is measured using covariance. So this is a covariance matrix. Covariance matrix becomes a what is that? Square matrix, because it depends on the number of variables, and it is a symmetric matrix. I said, the moment you get a symmetric matrix, you can solve certain things, you can do certain things. It is easy. Okay? So it is easy. So this is covariance, because I need this for PCA and other things, that's why I introduced that. So every data, even though there are 100 measurements, you will get 2 by 2 covariance matrix, because you are measuring only 2 variables. You can write this. Suppose if I call this as a data matrix D. I want 2 by 2 matrix covariance. What should I do? Suppose this is 100 by 2. You know the relation covariance, how to write, like, for example, I want 2 by 2. D transpose D is what? D transpose is 2 by 100. 100 by 2. You get 2 by 2 matrix. Corresponding your statistics, n or n minus 1, averaging you have to do. N minus 1 gives you called unbiased, etc. Let us not go into that. Either you divide by n or you divide by n minus 1, so that becomes a covariance matrix, right? So once you get covariance matrix, okay, you can do something else now. Okay, so we were here where 0 input gives you 0 output. I was looking at matrix from the system perspective or a mapping perspective, right? So there is also the moment A is there, there is A transpose. There is A transpose, right? A transpose is also a matrix which maps what to what. Suppose A is M by N. A is M by N matrix. What is a mapping? What is this vector space? What is this vector space? Suppose everything is real setting. Okay, A into X equal to B, right? A is M by N. What is X? What is its size? For it to be compatible, matrix vector multiplication, right? This should be n rows, one column. What is B? M rows, one column. Okay. So if I say this is X, X is n by n vector. X is n vector means what? This is what? This is Rn in the real case. B is in the M vector. This is Rm space. So every matrix AMN maps Rn to Rm. What happens A transpose? A transpose maps Rm to Rm. So you have to identify these type of mappings. Okay, so you want, okay, I don't want, okay, we were discussing row space, column space. There is something called null space of a matrix. What is null space of a matrix? What is null space? We know AX equals to B is our non-homogeneous system. I make AX equals to 0. That means if you have any vector X, A maps X to 0. You give any vector, including 0 vector. 0 maps to 0. Any non-zero vector you give to the X that maps to 0, then X, the set of all X, the solution, right? This is a solution. This becomes a null space of a matrix. Okay, null space of the matrix. The another one is range space. What do you mean by range of a function? Suppose f of x is a function. X is in the domain. For each x you get f of x. F of x is in the range. It is in the codomain space. Okay, it's a range. So Ax equals to B. B is in the range space. B is in the range space. Now what I want range space means set of all B I want, such that there is an X for each B. Right? That becomes a range space. Now, okay, there's a null space. So there is a range space. How should I just keep R? Maybe I'm using the notation, right? Null space is a subspace of the domain. Range space is a subspace of the, range space is subset of the codomain there. Codomain. But what happens is, when this is a vector space, null space also becomes a vector space. We can show that, but I am not going to the mathematical detail. All these become vector spaces. That's what my point is. It's a matrix which links between two vector spaces. Okay, so that is there. Okay, now the moment it is a vector space, we can talk about their basis and dimension. Right? Every vector space has a basis and dimension. Right? So if null space is a vector space, it has a dimension and basis. Range space also has dimension and basis. Okay. We call null space dimension is nullity. That's called, a term is there, nullity. Okay. The dimension of the range space is rank. So what is rank of a matrix? As far as vector space is concerned, for every matrix A, there is a range space. Range space has the dimension that becomes the rank of the matrix. So there is a fundamental theorem in linear algebra. It is called rank nullity theorem, right? What is rank nullity theorem? I'll just write this. Suppose nullity is something you call nu or whatever, the way It's a number, right? Plus rank, row. This is equal to number of columns, n, or it is the dimension of the domain. Domain is Rn. Dimension of the domain is n. Number of columns, that is almost. Okay, how do you get the rank from the given matrix? How do you solve for rank per se? If I give you a matrix, how do you solve for rank? Again, you have to go back to the echelon form. Echelon form. So, in the echelon form, suppose given a matrix is there. Okay, you do some first non-zero column is there, make it 1 in the reduced case. It may be some same 1, it may be 1 and 1, something like that. After that, you make it 0, etc., etc., you will get. Right? What is rank? Rank is nothing but the number of non-zero rows in the echelon form. That happens to be the same as number of pivots. If you know a little bit more linear algebra, that becomes. Okay? So now, if you call row rank and column rank separately, row rank and column rank become the same, that becomes the rank of a matrix. And also you know that if it is a 3 by 4 matrix, so rank is less than 3. Less than or equal to 3. 3 by 4. Otherwise, if I have 4 by 2 per se, 4 by 2, I have only 2 columns. Rank should not exceed 2 here. Right? Rank should not exceed 2. Okay. But another case of, as I was talking about simple matrices, you can generate matrices which are simple, that is nothing but one rank matrices. If a matrix has a rank 1, it has a nice structure. It becomes, how do you generate rank 1 matrices is by the outer product. You know the inner product is a dot product between the two vectors. Do outer product. What is outer product? How do you do? Suppose given vector x is 1, 2, 3. Okay. Your suppose another y is 5, 6, 7. You know x dot, rather it is inner product. Okay. What is inner product of x and y? It is your dot product. One of the inner product is dot product. You have x transpose y. You get a one scalar, right? Now I want outer product. Outer product. Here it is x y transpose. You get a matrix. That matrix is one rank matrix. For any outer product you generate, it becomes a one rank matrix. One rank matrix, you might have heard of rank deficient. Maybe it becomes a more advanced linear algebra for them. Rank deficient system, like that means not a full rank. Okay, what is full rank then? Suppose I have a square. Rank is defined for both square as well as rectangular matrices. It's not just for a square, like I can have 3 by 2, 2 by 3, 1 by, I'll test you. What is the rank of, what is the rank of this one? By definition or by the procedure that we used to find rank, you do echelon form on this. This row is dependent on this row, twice this. So this is dependent on this. Here also it is thrice this. I can just do this. You get 0, 0. You'll end up in only this. What is the rank? 1. Rank is 1. Right, like that. Similarly, if it is like this, what do you do? Here m by n, m is 1. There are so many columns are there. Okay. Now I want what? How do you say this? What is the rank of this? It should be less than or equal to 1, right? It should be less than or equal to 1. Right? So since there is a non-zero row, rank is not a 0 here, it has to be 1. It has to be 1. What is zero rank matrix then? Can you give an example of a zero rank? Maybe very degenerate kind of just testing you whether you have understood or not. Like whether what is the use you don't know that. You consider zero matrix. Zero matrix. The moment I put one thing, very simple matrix is what? Very simple matrix. Only one entry. That is a scalar. What is the rank of this? 1. Rank of that is 1. That's all. Like that. Okay, fine. So now rank nullity theorem is over. Now what I have to say? How much time I have? I'll just give you dimensionality reduction. We had 2 feature vector, right? 2 feature vector. What is the dimension of this space? Okay, you want to plot this data in some Euclidean space. What Euclidean space you plot? That's the first requirement now. The moment you have data, people say that plot and see, plot and observe. Okay, how do you plot? You have 100 data of height variable and weight variable is there. By convention, what do? We choose variables on the axis. Height, weight, plot that. You will get some scatter plot. Each is a point. It's a 2 vector. X and Y, H and W. Something like that you may get. You may get a cloud of something like this. Data. Fine. Now, this is a 2-dimensional data. Right? 2-dimension. Dimension you understand. These are the dimensions. 2-dimension is that. Now, dimensionality reduction means what? I have to reduce the dimension. From 2-dimension, can I get 1 dimension? And how do we get and for what? Etc. Maybe, very loosely speaking, to get 1 dimension, you can discard this per se. You lose information. You can also discard this one and you retain this, either of that. You lose information. But here I don't want to lose that much information, but I smartly have somehow reduced the dimension. What do we do is the thing. For that, what we do is, we have covariance matrix from the data, right? Covariance matrix. Okay, we have to diagonalize the covariance matrix. Okay, there your eigenvalues, eigenvectors comes into picture like. Okay, I'll just tell you I don't go into the math aspect of that because that may not be interesting to you. What I do is, you understand projection, right? Projection is a concept in vector space again. A one vector is projected onto the other vector. Okay, it is, suppose I have one vector, I have another vector, I have to project, suppose this is A, this is B vector, project B onto the A. How do you project? This is not an oblique projection, but it's an orthogonal projection. Okay, this is a projection. Projection is a scalar. I make it vector by unit vector in the direction of A. Okay, you know that this is theta, you know cos theta. Cos theta is what? This is adjacent, hypotenuse. Cos theta you know. So you get a nice relation. A dot B is what? Length A, length B, cos theta is the expression you get. Depending on that, you say whether angle is 90 degree, the dot product is 0, because cos 90 is 0, right? Cos 90 is 0. Maybe I'll ask you a quick question. I have this vector. I have this big B vector. How do you project this onto this? How do you project this? What happens? The moment when I give you one vector, it represents the entire line here, right? This is a space in which this is there. Okay, this is in the same direction of this vector. So I have to have a projection. This is your projection. In the unit vector direction is what? In the unit direction. A vector in the direction of the unit vector. Right? Like that. The other one is your simple this one. Suppose I give you one vector here. The other vector is this. What is the projection here? You are projecting a vertical vector onto this. Projection is just this. Point has zero length. Point has zero length. The projection is zero. Projection is zero. Okay. Fine. So, you understand projection. Once you understood projection, suppose I'll tell you, I'll give you this example. You have some data here, 1 point. You measured one person height and weight. I want to project this on, this is height, this is weight. The definition of this point is it's nothing but projection along H and W axis, right? So if this is a vector, you know that how to project this onto H. Okay, this is your height. Okay, you project onto this is your weight, right? Same principle I use. Now what I do is, instead of, this is my original, I want to project this onto something like this line. I'll give you one extra line, okay? This is a subspace also because it passes through the origin. I want to project this vector per se, A vector, onto this line. Again orthogonal projection. Project orthogonally because this angle is 90 degrees. So that given a point, I can project. By definition, the coordinate is nothing but projection onto the standard axis. Otherwise, I can project it onto any line. Maybe a vector space, maybe a affine line also. Affine means somewhere in the line. Okay. Now, you see this cloud of data points. It is in 2 dimension. But as you said in our Professor Raj's lecture also, he was talking about principal axis. Suppose this one is there, what is the principal axis is this, he said. Okay, there's an intuition there. Here, what is the principal axis? Just without going into the eigen and other things, I'm trying to get an intuitively principal axis. Like, you can have something like this, right? Where, okay, this is a variation of the, variation means a spread. The data spread is that. Okay, this is data spread. Now if you take this as a principal axis, you see the spread this much. That means more variation is there. More variation means more information. Maybe more energy also, square term. More energy is there. Right. Look at the other orthogonal axis per se. Okay, but in that case actually that has to pass through the origin because I'm just making a simple diagram here. Precisely that has to pass through because your principal axes are from the eigenspaces. The moment eigenspace is there, you can have a vector which passes through the origin. Vector space is there. Okay, like that. The other structure which is orthogonal to this, that happens in where? Covariance matrix, which is symmetric matrix. You know the eigenproperty of symmetric matrix. Eigenvalues are real. Eigenvectors corresponding to non-zero eigenvalues are orthogonal, distinct eigenvalues. Eigenvectors corresponding to distinct eigenvalues are orthogonal. It's very nice for a symmetric case. That's why symmetric matrix is always diagonalizable. So you can convert symmetric matrix into a simple system. It's a diagonal system, right? So in this, so principal axis means eigenaxis. This axis may be the eigenaxis corresponding to the largest eigenvalue. This may be to lambda 2. Here lambda 1, I put this greater than lambda 2 here. Okay. This is eigen corresponding to lambda. Eigenvector E I write, E lambda 2 is maybe. Now, you know the variation along this axis is this much, very less. So wherever variation is less, probably you can discard that axis. instead of discarding either H or a W, in this axis you are. Otherwise you are discarding along H or a W axis. Here I have got a new axis, the eigenbase coordinates. I can discard, I know that this energy is more, I don't want to discard this because I lose more information. But here the energy is less or the variance is less, so that I can discard along E lambda 2. Okay, suppose there is a point here, a data point is here. How do you project this onto the new axis? Orthogonal projection. Okay, so you have to project onto this one. The variation is this much. Okay, you project onto this, the variation is very small here. So that what I am saying is, on the new system, you get again two components. One is this, I'll call, I need something, my data, D, some D along lambda 1, D along lambda 2 I'll call. Again you have D and D lambda 1 and D lambda 2 for each points. Right? Here also we had, the numbers were there. But what I do is, since this is a principal axis which preserves more energy, I'll retain this. That means corresponding to this entry I'll have all this. But I'll make this 0. I'll make this 0. Right? That can do. Component. So you are reducing from 2 dimension to 1 dimension. So you have reduced. In the SVM and other cases for solving nonlinear classifiers, usually to make classifiers linear in the higher dimension, you do the other way. You go from lower dimension to the higher dimension. Okay? One is coming from higher dimension to the lower dimension, dimensionality reduction, compression, whatever. There could be loss is there, but loss is minimal in this case because we have chosen eigenaxis instead of discarding any of the H and W. Okay. The other in SVM and other classifiers is to make the classifier linearly to make the patterns linearly separable. For example, again I have a feature axis. There are some features like this. What is classifier? You have to have certain parabolic function like this, quadratic. Quadratic is a nonlinear function. Can I use now the question is, can I still use a linear classifier? What the trick you have to do is, you may go from here only 2 axes is there, 3, 4, okay. Suppose you have X and Y. X is a feature, Y is a feature, maybe XY product is a feature. Right? So you'll get another axis where what happens in the third dimension, this may becomes this and this may becomes X, where a linear plane can separate those two. It's linear separability there. For that purpose we go for a higher dimension. Okay. A more example that gives a feeling is this. Suppose a classifier can be this function, right? A circle. Circle is a nonlinear, right? You might have data points. One data point is here. The other could be this. I have to design a classifier. That means what? I have to design a function. That's a circle. That circle is learnt from the data. Data is plus on that circle, small, O. Okay? That's what learning is. What is learning? Given the data points, I need to learn a function, circle, so that I can classify. So here, the classifier is a circle here. But circle is a nonlinear function there. But if you go to the higher dimension, maybe, I just for the illustration I write higher dimension. These circles may be here, these may be somewhere plus, so that I can have a linear separation between the two. Linear in higher dimension, what happens? On a plane it becomes a line. On three dimensional, it can be a plane. plane, it is called hyperplane classifiers. That's what it is. Okay. So, given a classification problem, what do? You collect the data, maybe to reduce the data, if you use PCA, principal component analysis, this is PCA, you can go for a eigenbasis kind of a representation and discard depending on the variance, so that you can reduce the dimension. That's one thing. So other things is you can go to the higher dimension for classification in SVMs and other things. You use this technique, so that is there. Many times what we try to do is we design a simple linear classifier using, okay, suppose if I want to use a piecewise linear somehow I can design probably, but at point what happens is I have to design like this piecewise. You know that for any curvature a tangent approximation can be done. If you have infinite tangents, exactly the curvature you get. Same trick here, like you can have many linear classifiers so that you can get whatever the function that you want. Okay, that's what PCA and this is. I didn't go into the math detail for this, how to get in this one. There is a diagonalization theorem is there. So one theorem is like every symmetric matrix can be diagonalizable at least. So that is nothing but your called spectral theorem, also in your linear algebraic terms. The spectral theorem, more generalized version, becomes your singular value decomposition. So using singular value decomposition per se, any matrix, here the particular case is symmetric matrix. Symmetric is a diagonal matrix. If I have any rectangular matrix, I want to diagonalize this. I'll just give you an illustration what that means, okay? And then I'll stop. Suppose this is a tall matrix. Depending on your underdetermined, overdetermined, you get these two cases, right? Forget about the diagonal system. Now I want to convert this into a diagonal matrix. How do I do? And how many diagonal elements are there? Per se, this is 6 rows and 4 columns. You may say there's a 4 by 4 one thing I can get like that. May work. But actually what is happening there? Here it is 4 by 6, 4 and 6. Again you say 4 by 4 is a square system like. But actually what happens is, in both the cases the link is a rank. Okay, link is a rank. Rank is a number which is less than or equal to minimum of the rows or columns. Okay? Only retain that much of rows and columns. Okay, remaining maybe zeros. Okay? So what happens is, suppose here, even though this is 6 by 4, rank is 3 per se. 3. Okay? Here I also have to rank order the eigen values. If I say lambda 1, lambda 2, lambda 3, like. Okay, there are things like that. So I can have this entry, this entry, this entry per se. They come at this one. Okay, here I have to make it diagonal so that these entries are present. Okay? Even then this becomes 0, these becomes 0, these become 0. Okay? Only this entry will be there. So like that, diagonal, because other entries are zeros here. So any rectangular matrix can be diagonalized using SVD. There you need left and right kind of what Professor Dunn was telling, inverses like eigenvalue, eigenvectors like it is there. So that you need 2 side by side matrices so that you can do the diagonalization. That's very interesting, because probably that's the total, as Professor Dunn said yesterday, the entire linear algebra least square. The least square is that one only, and pseudo inverse is what? Derived from this one only. Okay, pseudo inverse gives you the general solution, like, okay, whether it is square system, full rank, or a rectangular system, rank deficient. Okay, pseudo inverse is one solution which is very optimal solution. Okay, very optimal solution for everything. It answers sort of every question there. The one answer is pseudo inverse. That's all. So if you know pseudo inverse, you have inverted the matrix. I'll come to the first point there. Our aim is to get 1 by A type of a thing, inverse. So you got the matrix inverse somehow, so that you are solving for variables x. Okay, so I started with that, I end with that. Okay, any question? So in between there are so many things, as done told earlier also, it takes more than 30 hours of lectures to what? To tell every point and make you understand step by step, like it's a one full course. So but anyway, we have ran through this. Fine, I'll stop here. Any question?